Okay, we can start now discussing about quality of service. We already said something about that. What means quality of service? We need to keep going a little bit more in depth. So we have said several things already. We already described the fact that one issue is that different type of traffic require attention to different type of parameters. The two examples, we have seen many of them in the previous hour, but phone calls, for example, require a fixed guaranteed bit rate, very low delay, and low blocking probability. Data traffic requires instead low or negligible loss probability. And we have to remind two important things. The first one is that providing quality in an heterogeneous environment is more difficult. So we are dealing with traffic heterogeneity, and providing qualities to unpredictable traffic is more difficult. And this goes with the concept of traffic characterization. So characterizing the traffic is important. The more we know about the traffic, the better we can hope to control it. And having heterogeneous traffic makes the problem more complex because we have to deal with different requirements, different type of traffic and different requirements. And that will make the scenario, of course, more difficult to be controlled. In this graph, we have two types of heterogeneity in traffic dimension which are shown. Of course, this should be taken as order of magnitude. And one dimension is connection duration. So one issue is that we may have connection which lasts very little, and other connection which lasts for hours or even more than hours, okay? So that's one thing that we have to take into account. So we may have connections which last for a very long period of time, and other which are coming and going, coming and leaving, and this is one problem. Another heterogeneity clearly is in the bitrate which characterize the different applications. You see that the bitrate can vary by several order of magnitude. So there are applications which require few kilobits per second, for example, the telemetry application, in which you have sensors which periodically send some information, but this can be done with a very little, very small bitrate requirement, and then you increase, right, data traffic, voice, video telephony, video conference with low quality, medium quality, high speed data transfer, etc., and you see that you may have, even within a single application, few order of magnitude in terms of bitrate needed to send the information. And this is one issue. The other issue is the traffic characterization. Now, suppose that you want to know something about the traffic generated by the user. The question is, which are the parameters in which we are interested in when we want to describe and characterize the user traffic? And actually, there are at least two main types of user behavior that we want to characterize. The simpler one is the so-called constant bitrate source. Now, the constant bitrate source is fully characterized when you look at the data flow once the connection has been opened before it's been closed, which is the bitrate of this source. If you want to be a little bit more precise, when you know the bitrate and the data size, the connection is fully characterized. You perfectly know the connection, the data generation process while the connection is active. Example of that, well, typically so let me call pi the data size and ti the time interval between two consecutive datas. Okay. Now a CBR connection is such that for any I, the ratio between pi and ti is a constant, and this is the CBR bit rate. This is bit over second, right? So that's exactly everything you need to characterize this source. If you know the bit rate and you know a given data size, you know everything about the source. You know exactly how the data will be generated by the source. In the case of the PCM companion coding for voice, which is the standard one, you have PI being equal to 8-bit, and you have TI being equal to 125 microseconds. And the ratio is 64 kilobits per second. Okay? If you instead generate according to a similar scheme, but through ATM cells, PI will be 48 bytes, and TI will be 48 times 8 times 125 microseconds. No, sorry. No, sorry. 48, that's a mistake. Where is the... Oops. PI is 48 bytes, and TI is 48 times 125 microseconds. Okay? So it's a fully known data generation process. You know exactly when data are going to be generated. So you know everything about this source. Okay? An uncompressed video is the same. If you don't compress the video, you take the video size in terms of number of lines, number of pixels per line, number of colors, quote at which you want to represent the chrominance and the luminance. You can come out with the number, which is a fixed amount of data you generate every 1/30 seconds if you have 30 frames per second, etc., etc. Exactly the same. All of them uncompressed voice, video, audio, or any regular data generation process is characterized as CBR, source constant bit rate, with a single parameter, if you know the data size. Okay? So it's completely predictable, unless you talk about something else which is not related to the description of what's going to happen when you generate the data, but in terms of how long this call will last. So the call duration is typically not perfectly known, and also the call generation process, which is how successive call will be generated, is not known in a deterministic way. So the deterministic part is what you do when you generate the data, and then there is a stochastic part, a statistically known part, which is the call generation process. So coming back to this picture, if you enlarge your time scale here, and you look at the different calls, so this is the call inter-arrival process, and within the call we know everything. We know that this is how we generate the data. But how many calls we generate, how long the calls last is known typically only in a probabilistic way, in a stochastic way. Okay? So the unknown part is the call. Within the call we know everything. Okay, that's one type of source. Now how about other type of sources? How do we classify them? Well, in general, the other type of sources are called variable bitrate. They are not constant in this way. Okay? Now when you move to variable bitrate sources, how to characterize them becomes more complex. More complex. Now, one approach can be to say, okay, I want to characterize them again through a bitrate, and one bitrate that you can, suppose that you don't want to do that a priori, you want to characterize this connection a posteriori. You may say, okay, I take the data generation process of the user, which in general is strange. I don't know how it is. It's something like that, right? It's non-regular. Maybe something like that, right? That's a variable bitrate. It's not constant. You see that the spacing is not regular, even if for fixed packet size. You may say, okay, I take the full connection, That's the connection duration, okay? I compute the amount of bits sent in this period of time. So this is capital T. I know how many bits have been sent. This amount of bits divided by T, that's the rate. The total amount of bits you send over time. And that's what rate it is. That's the average rate of this source, right? On average, I send at that speed. I send 1 megabyte over 1 second. The bit rate is 1 megabyte per second, correct? 8 megabits per second. Clear? That's easy. That's easy to be done a posteriori, not so easy a priori. Okay, maybe before starting to send the data, you don't know this parameter. But clearly, the average rate is something that it can be defined. Okay? Now, which is the average rate of a CBR source? Well, it's the rate which characterizes the source, right? If you take the previous picture here and, oops, sorry, this one here, and you take again the connection duration, you do the computation, and you will turn out having exactly that bit rate, which is pi over ti. Okay? Clearly. The first point is, how do we know the average rate? Because the previous rate is depending on the coding scheme we use to represent our source, right? So it can be 64 kilobits per second for GSM, we know it's a different value, etc., etc. But in this case, for a generic data generation process, knowing the average rate may not be easy. Okay? It may depend on many things. It may depend on your source, it may depend on your access link, it may depend on how much processing you are doing on the source that is generating the data. It may depend whether you have to access the network to a multiple access scheme or not. Maybe you are accessed through a LAN, and in a LAN, you know, at least if it's a shared medium-based LAN, you don't know exactly which is your bit rate, because your bit rate will depend also on the other user behavior that you don't know. So the average, even the average rate, which is simply to define, it may not be easy to be known a priori. Remember that from our point of view, we want to characterize the user traffic, because the more we know about the user, the more we hope to be able to control. That's what we are looking for. But we need these parameters before the user starts generating the data, not a posteriori. A posteriori is too late. Okay? So the fact that the average rate is not easily or trivially known in advance, it's an issue. And the other issue is that defining an average without specifying over which time window you measure it is a too weak information. Suppose that you have a connection that lasts 1 hour. Suppose that you know that the average rate is 10 megabits per second. What's going to happen on a shorter time scale is almost unknown if you only know these two values, right? Because the duration of your connection is so large that knowing the average rate does not give you basically almost no information about what's going to happen in this short time here. Suppose that this duration is 2 hours. We need to control the traffic generated by the user on a much shorter time scale. But 10 megabits over 2 hours, if you look at what's happening in, I don't know, 10-second time frame, it can happen everything. It's completely uncontrollable, right? You can have no traffic at all, no problem. You can easily compensate in the remaining time interval. You can have a huge transfer of data in that 10 seconds, okay? And then you can have very little traffic in the remaining 2 hours, and all of them satisfy the 10 megabits per second average requirement. So if the time window over which you measure or declare or check the bit rate is too large, that information is not specific enough. So you need to add, when you characterize a source stating which is the average rate, you need to add also a time window over which you measure the average. Okay? If you don't do that, stating that you are running on average at that bit rate is a very, very weak information from the network control perspective. Clear up to now? So that's one rate that we would like to have. So if you want to specify the average is good, but tell me also over which time window you ensure that this average is measured. Clearly, the shorter this time period, the more controlled will be your source behavior. Because every 1 second you must generate 10 megabits per second at most. If instead you have to do that every minute, after 1 minute it will be the same, the amount of bits you have generated. But within each second in this minute you can have a much more bursty behavior, right? Uncontrolled behavior, which will make, of course, more difficult to control this traffic in your network. So the time window over which you measure the average is very, very important. Another rate which is coming out, which is very easily definable, is the so-called peak rate. Now, what is the peak rate? You take every TI, the TI is the spacing between two packets, okay? And you take the minimum. Suppose that the packet size is fixed for simplicity, okay? If you take the minimum TI and you compute PI over TI, that's the highest rate of generation of this source. That's called peak rate. Over the whole duration, the highest speed you have generated is the distance between the two closest packets. Okay? Clear? Now pay attention. When you generate packets, in order to define the source speed, you have to look at the distance between two packets. This is what characterizes the source rate. Why I'm saying that? Because if you consider the same source generation process, okay, so suppose that the user is generating two packets with this spacing, okay? Now, suppose that you do that on link A, and now you do that on link B, so you change the access speed at which the transmitter of the user is generating data. You change the link speed. So link A was going at 10 megabits per second. Now you increase the link speed, you double it. You change the transceiver, you change the link medium possibly because you need to have a better quality. And now you move to 20 megabits per second link speed. Okay? But you have the same application, the same generation process. What would you see here on this link is that this packet duration, which is what? How it is called? This packet duration on this picture is what? Is the packet transmission time, okay? This is the packet transmission time. Now, if you increase the link bitrate by a factor of 2, the packet transmission time will decrease by a factor of 2. So you will see in this picture something like that, right? The packet size is reduced by half, correct? But you see that the spacing between the packets is not changed because this is what characterizes the user behavior, not the link speed. So you don't have to look at the bit rate transmission when you send a packet to characterize the source. This has nothing to do with the source behavior. This is the link characteristic. This is another issue. You have to look at the spacing between adjacent packets. Okay? Now, if you had a source in case A, which is generating two packets in this way, this source is really generating at the peak rate, which is 10 megabits per second, because the spacing between two packets is the minimum possible one. You are filling up your link with back-to-back packets. That source behavior speed is 10 megabits per second. That's correct. Not because you are sending the packet, the single packet at 10, but because the two packets are back-to-back. So if you take TI, this PI over TI will give you exactly 10 megabits per second. And indeed, if you will change now to link B with the same source behavior, you will see that still the bit rate which characterizes this source is still 10 megabit. You see? Now there is a spacing because it's nothing to do with the link bit rate. So in order to characterize a source rate, you have to take the distance between consecutive packets. Okay? The inverse of this distance multiplied by the amount of the packet size between the two packets is the instantaneous bit rate. Okay? Which is completely independent by the link speed. Of course, you cannot have an instantaneous rate larger than the link speed. So the peak rate is easily boundable. If you have no idea about what you are going to do, you can know that the peak rate when you generate the data is your link speed. Because the worst thing that you can do is to send packets back to back. And that bit rate will be the link speed. So the peak rate is easily known for the source. Maybe you are going to generate less than that, but for sure not faster than that. Because the best you can do is to put two packets back to back, and that's an instantaneous rate equal, in that case, to the link speed, which will be 10 megabit in case A, will be 20 megabit in case B. Okay? But the characterization is done by looking at distance in time between packets, consecutive packets. Now the peak rate is the fastest instantaneous rate you experience in the whole connection duration, and easily bounded by the link access speed. Okay? Is it clear? Okay, so to characterize VBR sources, we have more complexity required. For example, we would like to have an average rate, hopefully, if you know it. We would like to have a peak rate, or a ratio between the two, which is called burstiness, the ratio between peak and average. Now, clearly, the larger the difference between the worst case behavior, which is the peak, and the average one, the more unpredictable will be your traffic. If the ratio is 2, if you compare the average behavior with the worst case, you have just a factor of 2 in terms of difference. So it's fairly smooth traffic. If the ratio is 100, the difference in speed between your average rate and the worst case rate is a factor of 100, which is a huge number. So the ratio between the peak and the average gives you what is called the burstiness source, which is related to its unpredictability. You know that there are bounds, but these bounds are very large. So since the bounds are very large, the real current behavior can be very variable. Correct? Can range from the average to the peak. Take into account that if your peak is 10 times larger than the average, suppose that the peak is 10 times larger than the average, so the burstiness is 10. Okay? It means that the difference in rate that you will see as a network is more than 10. Because if you are running 10 times faster than the average, sooner or later you need to run less than the average to go back to the average rate. Correct? So if you increase your speed above the average, sooner or later you have to go below the average to come back to the average rate. So the difference is going to be more than 10 from the more active period with respect to the more inactive period. Okay? Can be much more than that. The larger the burstiness, the more unpredictable is the traffic, the more difficult to control is going to be. That's the message here. Okay? So let's take some examples. So suppose we are considering link speed of 100 megabit per second, okay? All of the pictures I will show are referring, and suppose they are scaling properly, assuming that the link speed is 100 megabit per second, okay? Now let me create a picture here in which we have this source, and suppose that we have, this is a period of time which I call 10, in which you have one, are active one over 10, and you are inactive for 9 period of time, okay? Then you are active for 1, and you are inactive for 9. 9 is 9 packet transmission times, okay? So you take a frame of 10 megabit, 10 spacing, and you are active for 1 packet transmission, then you are silent for 9 period of time, and so on and so forth. And you will keep repeating this behavior forever, okay? Which type of source is this? This is a CBR source, correct? And which is the average rate of this source? Or also the peak rate. For the CBR source, the average and the peak are the same by definition, because you keep having the same rate instantaneously. Which is the instantaneous rate, which is also the average rate? It's 10, right? You are active 10% of the time. The link speed is 100, so the actual rate will be 10 megabit per second. Okay? Now, this source here, you are active for 2 period of time, and then you are silent for 18, and then again 1, 1, 18, and so on and so forth. And you keep repeating it forever. Okay? That's another example. Same link speed, 100 megabit per second. Which type of source is this one? We have only 2 choices, right? So it's CBR or VBR. Here it depends, it doesn't work. Who is voting for CBR? Raise your hand. You cannot abstain, otherwise you will get 2 points less at the exam. So who is voting for CBR? Raise your hand. Who is voting? Raise your hand. This way, not this way. You know. This way. Who is voting for VBR? Come on, I said you cannot abstain. Who is voting for CBR? Raise your hand. Who is voting for VBR? Raise your hand. No, don't be shy. Raise your hand a little bit more. You're still abstaining, even with the camera. Okay. This source is actually VBR, even if it looks like CBR, so most of you were wrong. Why is VBR? Because you have to take spacing between packets, and you see that the definition of CBR is that any pair of consecutive packets, this is a fixed packet size, should have the same time distance, right? The same TI, like in this case. The TI is 10, always. In this case, you have 2 TIs here, which are different. This is T1 and this is T2. So by definition, you have a peak rate, which in this case is how much? Which is the peak rate of this source? If you have 2 packets back to back, the peak rate of this source is the link speed, so it's 100 megabit per second. So it's VBR with peak rate 100 megabit per second. And which is the average rate instead? Long-term average. Yeah, it's still 10 megabit. Why? Because you are still active 10% of the time, right? You are active 2 every 20 time slots. So the activity period is 10% of the time. Since the link speed is 100, the average rate is going to be 10 megabit per second. So the same average rate of the CBR source, which is 10 megabit per second. Okay? So it's a VBR source with the same average rate of the CBR source, okay, but with a peak rate which is in this case 100 megabit per second, which is bounded by the link speed. You have any question? I'm here to try to answer to them. So. For the average rate, okay, the average rate is the amount of bits that you send over time if you don't bound with a given time window. In this case, you should take the full duration of the source, okay? The peak rate is clear. The peak rate you take 2 consecutive packets is 100. Now, if you look at this average behavior, you see that this source repeats itself in the same way every 20 slots. And over these 20 slots, you generate 10% of the time, and then you do nothing. So your activity period is 10% of the time, which is 10 megabits per second, okay?
But even though in this case we have 1118, 1110, we consider this.
No, this is an 18, sorry. This is an 18. No, sorry. I said 18, but I unfortunately didn't count. No, it repeats itself forever in the same way. 2 packet generation, 18 of silence, 2 packet generation, 18 of silence. So the picture was correct, but it was supposed to be an 18, but it turns out to be a 10. No, it's my mistake. Unfortunately, it's very slow when I write, so I should write much slower, otherwise these things happen. Sorry. No, that was an 18. And you keep repeating. Yep, sorry. Of course, otherwise it would change. You have to take the 2 periods and to do the measure. It will be different average rate, of course. And if you think a little bit about that, now if you consider some source in which you have, I don't know, 10 packet generation, and then you have 90 silence period of time, now this is not scaling in, and you repeat it again. So you suppose you generate 10 packets back-to-back, then you keep silent for 90. You think a little bit about that. This is still a VBR source, of course, which is characterized by the same parameter as above. You have the same peak rate, the same average rate. And that tells us that even having peak and rate, which is already not easy, sometimes it's not enough. Sometimes we will have some information about what is called the burst duration. How much time we are going to send to the peak. In the first case, it's going to be 2 packets. In the second case, it's going to be 10. So we will distinguish the 2 behavior. Clearly, this behavior here, the second one in terms of VBR sources, is much more difficult to be dealt with in the network with respect to the previous one. The first one is almost CBR, right? Yeah, formally you have a burstiness by a factor of 10, but at the end you end up having only 2 packets back-to-back, and then silence, 2 packets back-to-back, and silence, which is not so bad. Of course, if you instead get 10 packets back-to-back or 100 packets back-to-back and then much longer period of time, it's going to become much more difficult to characterize and control it. Okay? If you want to see it, so that's called burst duration. How long your burst, your peak rate is going to last. Let me put it in another way. If you were defining the average rate over a given time window, and this time window is short, you would make a distinction between this source and this source, right? So another way of distinguishing between sources without adding a burst duration parameter, it will be to say your average is measured over a given time window. In that case, the average of the first source, you see, is going to be different from the average of the other source. Why? Because you are measuring the average over a shorter time window. So this source is not going to be characterized by this average rate, because in this period you see that the average rate is 50 megabits per second. So it will not be a source controlled with an average rate of 10. So the other way of making your traffic more controlled, more smooth, even keeping the 2 parameters only, peak and average, is to say, okay, the average is going to be measured over a given time window. The shorter the time window, the more smooth is going to be your source. Okay? Clear? This is just to say that only peak and average is not enough to have a good characterization. You will need something more. Of course, the more you know, the better it is, because you can run more complex algorithms, you can have to hope to have better controlled network and better performance. Okay? Once you characterize a source with a given set of parameters, suppose that you use average rate, peak rate, and burst duration. Okay? So suppose that you have an average rate with not a time window, a peak rate and the burst duration, and indeed the burst duration is related to the time window over which you measure the average. They are not independent, of course. It's another way of giving a time window. any source belonging as bad as a source sending as fast as possible with respect to this constraint is characterized in this way. So what I'm saying is this set of parameters is giving you a worst case source. And you will typically consider any source characterized with these parameters as if it was behaving as the worst possible way. Let me go back. It's more difficult to say than to explain. Suppose that I give you, okay, characterization, CBR source at 10 megabits per second. Any source sending less than this is still satisfying this constraint, right? So you can take the worst case and assume that any source characterized in this way is behaving like in this way. You know that this is on the safe side. No source will do worse than that. If you have these parameters with burst duration 2, you can take this as the worst possible case and make your computation, and this will hold for any source characterized properly in this way, and so on and so forth. So any characterization actually gives characterize very different potential sources, but all of them are bounded by a worst case, and we will use this worst case in any analysis. So we will be safe for any real source. Okay? It's a worst case behavior once you give me this parameter. Real sources will be better than that, not worse than that. I will take the worst case. So you are typically characterizing a family of sources with these parameters. Okay? All of them are represented for our purposes with the worst possible source behavior which satisfy these parameters that you have declared. Still, as in the CBR case, you still have the unknown or the statistically known only behavior for what concerns the call duration and the call generation process. This is still a stochastically known scenario. So in the CBR case, at least once the connection is active, we know exactly what's going to happen. In the VBR case, once the connection is active, we still have a statistical behavior which we can bound through a set of parameters. And we will assume that the source will behave exactly as the worst possible scenario. Okay? Still we have the unknown about the data generation process, but we can bound it if you give me the parameters. How large are the bit burstiness? Well, it depends. It depends on the type of application that you have in mind. Here there are burstiness ratios which are very, very high, very large. Let's say that in practice having burstiness ratio on a factor of 10, 100, up to 1000 is possible, is really realistic in today applications. Potentially you can have a much larger burstiness factor, but they are not so common. So the most applications are here in this range here for very highly variable peak rates. Okay? That's another thing that we have to take into account that will make our task of controlling the network not so easy. So that's in terms of traffic characterization. Now in terms of networks, what we can say, well, we have said also on this side many things already. We will use mostly as an example tree networks as a kind of extremes, and the third one is something that allows us to move between the two extremes. So one extreme is the phone network, the fixed telephone network, plain old telephone system, which is based on circuit switching and which is supporting only one type of application, which is voice call. The other extreme is the plain internet with no QS features, which is supporting well data traffic and which is packet switching with datacom service, as you know. And the third thing that can be something that allows us to move between the two extremes is the broadband ISDN, which is a packet switching technique with virtual circuit service. okay, which can be a way of moving between the two extreme behavior depending on which type of algorithms we want to run, how much control we want to run on our network, etc., etc. But it will give us the potential way of behaving as close as we wish to the telephone network on the one extreme, or as close as we wish to the internet with no QoS features. So we know already something about the quality that we can obtain in this network in kind of informal way. Let's start to summarize it again. So let's start with the plain old telephone system, the fixed telephone network. First point, characterization. Well, we know that in the telephone system we have a CBR source. The users are only able to generate CBR traffic. So we have a full characterization when you generate the data. It's a 64 kilobit per second generation process with the data size fixed at 1 byte. So we know everything about the source apart from what concerns how calls last in terms of duration and how you generate call, which is the intergeneration process of different calls for a given user. The network is based on the circuit switching technology, which is providing a constant dedicated bit rate, which implies that there will never be congestion, because either you get this constant bit rate assigned to you, or you don't get it at all. But if you get it, it's guaranteed. It's only for you. You have the minimum possible delay in terms of network architecture, which is the propagation delay, because there is no additional delay in the intermediate nodes, because you are not doing any processing, any storing. And the loss probability is, if you have high quality medium, transmission medium is negligible or zero. Sorry, the loss probability, not the error. The loss probability is exactly zero, because you are never dropping data because there is no buffering. Instead, the error probability is small. It's depending on the quality of the medium. It can be few percent up to very, very little, depending on the quality of the transmission. Why is that? Well, because we are using a very specific switching technique which is suited for this generation of traffic. And because while you generate the traffic, we know everything, so we can easily control the network. That's why we obtain this high quality. This is exactly the quality needed by this application. We need 64 kilobits per second. You will give you exactly that one. You will minimum delay. I will give you the minimum possible delay. I want zero losses. I will never drop the data. So it's exactly a good match between what you provide and what are the user needs. One reason is that because we exactly know the user traffic generation process. However, we have some issues related to the possibility that we don't have enough resources when you want to make a call. Why? Because there is still a stochastic behavior. There is some characterization of the user which is not exactly known, which is how calls are generated and how call lasts, how much they last. And given that this is unknown, this is known in a probabilistic way, the consequence is that sometimes we may not have enough resources to guarantee this high quality. This will translate in blocking probability. So the issue here it may be in blocking. Sometimes we need to block our users because we don't have the 64 kilobits per second channel. And we prefer to say no to a new user instead of accepting it, having it, sending the data with the negative consequence of creating issues, quality issues to already accepted users, already accepted calls. That's a design choice. So we make the choice of refusing the possibility of coming in to new users to guarantee the quality of already accepted users. Okay? The unknown is in the stochastic behavior at the call level, the quality that we are not able to provide deterministically but only statistically is the call blocking probability, because the calls are not exactly known. Okay? Okay, so this is an example of very good quality. We are really satisfying user requirements. Whenever you get in, you are satisfied exactly with the quality that you require. The negative aspect of this is that, well, we trade a very high user satisfaction with a potential network utilization which is low. Now this may sound a little bit strange in the sense that we know that if we provide a 64 kilobit per second channel, the user is really going to use it all the time, right? You know how it works. You generate a pressure wave which is converted in an electrical signal. This electrical signal is sampled periodically by the network, and you generate 8 bits every 125 microseconds, right? Which is exactly what you need to satisfy and to fill up your link. So indeed, if you get a channel at 64 kilobits per second, your call is active, and it will regularly generate as a CBR source 8 bits every 125 microseconds. So the utilization is not low. It's exactly the utilization that you would expect to see. This is true if you do not consider the fact that those samples may not really represent user data. In a phone call, normally, which is bidirectional, so you have two independent channels at 64 kilobits per second in the two directions, typically, first of all, you speak only on the one end. So typically, just for this reason, of the two channels, you are going to use only one of the two. So 50% of the utilization goes off. It's very difficult to talk at the same time. And worse than that, while you are speaking, there are a lot of pauses which will turn out in a real utilization, if you consider only what the user is really generating, is roughly speaking between 25 and 30%. 50% is lost because you speak in a walkie-talkie way, right? Half duplex. And then a little bit more due to the pauses in your speech, etc., etc. And why is that? Because we are characterizing as a CBR source something which is indeed not CBR. The original source is not CBR. We are creating an equivalent CBR source by keep sampling and sampling the background noise and whatever. So it seems from the network perspective to a CBR source, but from the user perspective, this is not really what you are going to generate. The user is really generating a VBR source at a much smaller bit rate. You are translating it in a CBR at 64, but the real utilization of your network is very, very low, 25%, roughly speaking. So this is an example of a network in which a lot of effort has been posed in satisfy user requirement at the price of having a low link utilization. Okay? The other extreme is the internet. In the internet, what's happening? You have no source internet with no QoS features, the plain internet. Okay? You have no user characterization. Nobody's asking us what we are going to do when we want to access the internet. You do whatever you want, you wake up when you want, you don't even declare I want to connect with that server. You simply generate data with respect to this server, to the other server, to the third server, and you will get data from them in a completely uncontrolled fashion, right? There is no declaration of what you're going to do, not even in terms of bit rate, as we have said before, but even worse than that, in terms of what we want to talk with, etc., etc. You don't know anything. You may have a very vague characterization of a user. User, it depends on what user means in this case, right? Because in this case, user may be a single user, it may be a web server, it may be a data center, it may be a video server. So you have the very wide variety of users, and especially they are not declaring anything. So you don't know anything in your network. You have no idea about what users are going to do. You may have some vague statistical characterization, okay, but not on a given communication. Furthermore, the network is a packet switching with datagram service, which implies that on the good hand, we have a full sharing of resources. If I'm running a proper set of routing algorithms, I can send my data from A to B and spread out them on the whole network if I wish. So all of the network capacity is available for a single user, potentially. That's the packet switching with datagram. Remember, any packet follow any path. You don't know. If you want, you don't have this, but potentially that can happen, which is good in terms of resource flexibility. You can get as much as you need. But unfortunately, on the other hand, you have no idea about which is going to be the real bit rate that you get, because that depends on everybody else. The bit rate that I get in a phone network depends on my requirements and on the fact that either the channel is there or not. This is just a binary possibility. Either I get a call, can make a phone call, or I cannot. If I make it, the quality is guaranteed and I know it. In this case, you have no idea, because your performance in terms of bit rate and delay and everything else and losses as a consequence depends on everybody else. And nobody is declaring nothing to anybody. So it's completely unknown. So you may have congestion, right? Because you may have excess of traffic depending on user behavior, on routing policies, on many, many things. And of course, as a consequence, you may have losses. They may be negligible, but it may become very significant if you have a strong congestion scenario. Okay? So it's a completely uncontrolled network in which basically the user satisfaction can be very low, it's depending on everybody else, but at the same side, on the positive side, you have a very high network utilization. Okay? The error probability in this case, if we are considering wired network, is still very low, and the blocking probability on the good side is typically negligible. We never get connection refuse from the internet, right? We may get a very low throughput, which makes the application so unsatisfactory that we will close it, but the network will never say to you, no, you cannot try to send your packet because I have too much traffic. There's nothing is going to happen in the internet, right? You can always try. Of course, you can have such a low bit rate that you are completely unsatisfied, so at the end you will not be able to successfully run your applications, but there is no blocking formally, like in the phone network. In the phone network, sometimes you get the busy tone because you cannot get access to the network. Okay? So these are the two extremes. Is there anything in between? The answer is yes. And for example, and it's not the only one, but it's the most notable one in terms of the framework that has been defined in terms of standardization effort to support this feature, is the broadband ISDN. Why I'm saying it's intermediate situation? Well, first of all, we have the possibility of characterize the sources in a very complex way, if you wish, very varied way, because we want to support, remember, heterogeneous traffic here. The previous two networks were voice only and data only, so mono service. This is an integrated network, right? But we have the possibility of characterizing our source, either deterministically or statistically, probabilistically. And the technology we use is a packet switching with virtual circuit service. Now, in this scenario, we have some features of the packet switching with datagram, which are the possibility of sharing resources and as a consequence having a good utilization, which is not possible in the circuit switching, because in circuit switching, remember, we slice with a fixed size the cake, and if you are not hungry, nobody else can take your slice or portion of your slice. Whereas in packet switching, there is no slicing, or the slicing is continuously adaptable depending on the number of users, right? Here, we have the possibility of sharing, which means that if you need less, I can get more, okay? Which potentially can increase the resource utilization, but at the same time, the network is able to control the user connection, the user flow, because you know that there is the existence of a user flow, because every user communication is characterized by the virtual circuit. Whenever you want to send the data, you have to declare something to the network. At least say to the network, I want to connect with that guy, and at that point the network will know the path. So you know that you are going to share only on that path. Okay? Now, why I'm saying that you can have a behavior which ranges between the packet switching, the internet-based, and the telephone network? Well, suppose that you simply add the need of declaring I want to connect with that guy, and you do nothing else. You don't run any control algorithm. Your network will behave very similarly to the packet switching with datagram. The only little advantage is that you share only on a limited set of links. But if on this path there is a congestion, you will have a congested network, right? So if you do nothing else, if not asking the user to declare, I'm going to send data from A to B and using the labels to identify it, the behavior from the user perspective can be very similar to the behavior that you have with packet switching, with datagram service. So congestion, potential losses, no bitrate guarantees, no delay guarantees, etc., etc. But good utilization. And no blocking, if you wish. The only thing that you allocate is the labels. You have no allocation of resources, right? On the other hand, suppose that you add algorithms, control algorithms. So you may say that, well, I'm not going to accept any call. I'm asking the user, for example, to declare how much bitrate do they need, and so on and so forth. You see that you can start acting in your network in a way that is allowing you to control much better what's happening, up to the point, if these algorithms are so sophisticated, that you can even fully avoid any congestion. And if you avoid congestion, you avoid losses, and you can have bitrate guarantees and delay guarantees also if you control the level of load in your network. That implies adding complexity in algorithms to control network resource sharing, and also in putting requirements on traffic characterization. Because remember always, if you don't know what the user is going to do, controlling it is going to become very, very difficult. So you need to put more constraint on your user. The more constraint you put, the more sophisticated algorithms you can run, the higher the control can be. That's why this technology, virtual security, is a hybrid between the two. You can have features which are very similar to the one with packet switching with datagram, which means high utilization but lower quality, or on the other extreme, very high, tight quality for the user, if you're running complex algorithms, of course, but at the same time, with good quality provided, closer to the secret switching behavior. So that's the trade-off you can have. It's up to you, depending on how you run and you manage your control algorithm, the network behavior you can obtain. You have no choice in the other two extremes. In the other two extremes, you have no choice. There is no way of sharing of resources in circuit switching. It's physically not possible. There is no way of controlling the user quality, because you have no concept of user quality at the call level, right? Because you have no concept of call level in a packet switching with data. You don't know what a call is. You don't know it. You have no way of defining it, so there is no way of controlling it. You don't know which path the packet will follow in your network. So you need to make more complex network architecture to make a packet switching network to behave similarly to a circuit switching one. But you can do that. Is it clear? So that's why the vast majority of efforts in defining quality of service technique and standardizing them has been devised in the broadband ISDN arena, because we have the virtual secrets technique with packet switching. The effort done in the internet to provide quality, all of them are starting with the need of identifying what the user flow is, which means assigning labels and not using IP address to do something, to identify a set of packets as a user flow. And if you do that, then you can hope to control it. All of the control algorithm part are orthogonal to the technology you apply, as long as you are able to identify a user flow in your network. So the effort in the internet QoS are the same in terms of algorithm of the effort you can have in the ATM, in broadband ISDN, in friendly. It doesn't matter from the algorithmical point of view. But you need to identify the user flow, the user flow. And that's what has been done in the internet, extending the concept of internet packet in order to ensure that you can identify in some way what a user flow is, a set of packets. You need also to ensure that this set of packets is following a fixed path. Because otherwise, if you spread them out randomly through the network, controlling them it becomes impossible, and providing quality becomes impossible. Okay? So the most natural scenario in which to do that is a circuit switching, is a packet switching technique with virtual circuit service. Okay? So now we can say a little bit more about quality. We have also called the design problem. We want to provide quality. We know, and we gave as given, the network topology in terms of nodes and link speed. And this is a fundamental building block for the quality that you can provide. We will give this as granted. So we will assume that the amount of resources has been designed. Clearly should be designed having in mind a given number of users and a given quality model in mind. Otherwise, it's not independent. But when we talk about quality of service problem, we assume that the network has been designed. So the resources are given. We want to characterize user traffic. We need to characterize user traffic and user behavior. Given that, we want to jointly obtain a guaranteed QoS for each user connection, call, flow, whatever you want to call it, that doesn't matter. A priori, I want to guarantee that, ensure that before you start sending the data. Okay? It should be something that I guarantee to you, and at the same time, have a reasonably high network utilization. Okay? If you don't have these two goals joint, the problem becomes trivial. You take a worst case allocation, what we do in circuit switching. The quality is very highly guaranteed. It's very easy, fairly easy, even in a heterogeneous environment. Okay? I don't care about resource utilization. I can follow a so-called over-provisioning model. I put so many resources that I will never have problems of quality. And there are systems which are over-provisioning. Think about the water distribution network. Of course, I'm talking about areas in which you don't have water shortages problem. When you go at home and open your, what's the English name of that? The tap, yes, to get the water, you don't ask yourself, there will be water available, right? It, by definition, is there, right? When you switch on the light, the electricity is there, because those are over-provisioned networks. Networks that have enough capability to satisfy user needs, of course with some bounds, right? We have an electricity bound at our house, but within that bound, electricity is typically always available for everybody, unless something very, very strange happens. How this is possible? That's an over-provisioned network. The amount of available resources is so large that it can satisfy any user need. And in that context, everything becomes trivial. Okay, it's not an issue to say, okay, if I'm switching on this bulb, then the washing machine is not going to work, right? Washing machine and light have very different requirements. But both of them can be satisfied if I have enough resources. They don't go in competition. Even if there is an heterogeneous environment, I can satisfy everybody. Remember, a heterogeneous environment is difficult because I can have a bike, a motorbike, a car, a very fast car, a Formula 1 car, all of them sharing the same infrastructure, the same highway. And that becomes difficult because they have heterogeneous requirements. Remember this concept? We already discussed it. But if you have a highway with hundreds of lanes, who cares? Everybody is satisfied and they don't create competition for resources. That's the over-provisioning model. So if you have in mind an over-provisioning model for telecommunication, you can throw away 90% of this class and forget about it. Okay? Who cares? We put resources, we have enough bandwidth, we have fibers everywhere, we have enough bandwidth, and that's it. It's going to work for any application. And we don't have to worry about controlling and making all of these complex mechanisms of managing, etc., etc. Okay? So the difficult task is to have quality of service in mind, but at the same time you want to put as high as possible the network utilization. That's the difficult part. Okay? So we'll forget about this over-provisioning model that sometimes is used, maybe it's used in some portion of the network. For example, when you have an access LAN, typically that portion of the network is over-provisioned. Okay, you have more resources than what you really need in any situation, in any reasonable situation. Okay. So that's what we want to do. Jointly guarantee a priori quality, negotiable with the user, and at the same time, keep an eye on the network utilization that should become reasonably high. That's the difficult part. If only one of the two things are interested for you, it's easy. If you don't care about utilization, you follow an extension of the circuit switching approach, everything is going to work. Okay? And that's kind of over-provisioning model. If, on the other hand, you care only about utilization, packet switching with data can throw away as much as you want, and that's it. No problem. Okay? So that's what we are going to discuss for a few weeks about quality of service. You have any question about that? Okay. So Thursday, unfortunately, there will be no class. I know that you are very sad about that, so we will meet next week. I hope to have one recovery class next week. I will let you know because I didn't get an answer from the offices yet, because then we are going to skip some classes, and so I need to recover some of them.